Hello, this is Reza Hanggoro with Let That Sink In. What is the ideal center of mass for a cargo ship to not capsize in a rough ocean environment? So, the objective of this experiment is to test the different types of placements of weights on a ship's hull to test which placement would result in a greater hull stability. My hypothesis is a center of mass lower in the hull, along with positioning of cargo lower in the hull, will likely give a ship the most stability in the ocean. So, the testable question is, what is the ideal center of mass for a cargo ship to remain stable in an ocean environment? So, quickly before we get into the experimental procedures, in my research I found a few terms like bay number, a number that designates a specific cargo hold, row number, a number that designates where the cargo container is stored horizontally, and tier, a number that designates where a cargo container is stored vertically. Typically, cargo ships require an enormous amount of coordination and planning to function smoothly. The cargo containers are sorted by bay number, row, and tier. Heavier cargo loads are typically spread out throughout the ship horizontally rather than vertically, such as the picture here. You can see that heavy weights would be placed on both the left and right sides of the ship instead of the top and the bottom. Cargo ships are also specifically designed with security and safety in mind. Cargo ships use cables called lashing to secure the cargo to the ship and keep it more stable. Without lashing, the cargo could collapse off of the ship and cause a few problems. So this is a pretty basic diagram of a cargo hold. We've got three different holds, and there's a deck separating the different tiers of the holds. There's a front labeled as the forepeak of the ship, and there's a back labeled as an afterpeak of the ship. There's a bottom part called ballast tanks, which are typically flooded for stability, and there is a water line drawn where a typical ship would have a water line. So this slide is just explaining the terminology from the diagram. A hold, like a cargo hold, is a place where cargo is stored. Holds can be located anywhere around the ship, and cargo ships are typically designed to hold the most cargo in these. A lot of the weight from the ship comes from the hold. So a deck of a ship is a structure that supports walking for work, transport, and other activities, and typically there are more than one deck on a ship. The forepeak and afterpeak are the furthest front and back decks of a ship. These can be used for storage for ship stability through weight distribution. The ballast tanks at the bottom of the ship are usually flooded with water to add stability to the ship in case it gets rough in the ocean. So this is a pretty simple diagram of our experimental setup. We have one ship built with a low center of mass, one ship with a centered center of mass, and one ship with a high center of mass. So 3 model ship's hulls have been used to construct 3 different boats. One will have weights placed at the very bottom of the hull, one on the second layer of the hull, and one on the uppermost deck. A cardboard deck will be constructed and glued in order to place the weights on top or in the middle. The ships will be rocked gradually in a large tub of water to simulate waves. The waves will get larger and larger until the ship capsizes. So these are our experimental procedures. Step 1, construct or modify 3 model ship's hulls and add 2 layers of cardboard decks to the top, middle, and bottom of the ship's hull. Step 2, cut 6 inches of 2-inch PVC pipe and fill it with 180 grams of sand. Step 3, add 2 of these weights to the bottom, middle, and top of the model boats. Step 4, fill up a large tub with water and gently rock the tub back and forth to simulate waves hitting the ship. Step 5, gradually raise the intensity of the waves until the boat capsizes or the waves reach a certain height. And step 6, record data. So these are the pictures that go along with the last slide. So step 1, you just add weights to the top, middle, and bottom of the ships. Step 2, you cut out 6 inches of 2-inch PVC pipe and fill it with 180 grams of sand. Then step 3, place it at the bottom, top, and middle of the ship hulls. Step 4, you would have placed the ship on top of the water in the tub. Step 5, you would rock the ship around until it would either capsize or the waves got too high, which was 4 inches. And step 6, you would record the data in the table. So these are our materials that we used. 1, we used a hot glue gun and hot glue sticks. 2, cardboard. 3 model boat hulls that we modified. 4, play sand. 5, some PVC pipes. And 6, a large plastic container. So these are just a few pictures of the experiment setup. You have high, low, and mid center of mass. We've got a collection of our materials like the wooden tub, the glue gun, cardboard, and the boats, the hull and still water, where you would put the weights, and how you would measure the waves created. So this is the actual experimental process. You would, step 1, tape weights to the boat's hull, symbolizing the lashing. Step 2, place the boat in completely calm water. Step 3, rock the boat back and forth according to the blue tape's measurements, starting with half an inch, and gradually increase rocking motion by half an inch until the boat capsizes or reaches 4-inch waves. So here are experiment results. We have waves from 0 to 4 inches. The boat with the lowest center of mass did not capsize from 0 to 4-inch waves. The middle center of mass capsized at 2 inches, and the high center of mass capsized at 0 inches, still water. So finally, we have our conclusion. From this experiment, one can deduce that a ship's center of mass is incredibly important when carrying cargo or even constructing the ship itself. If a ship's center of mass is too high, it can be vulnerable to capsizing in an ocean environment. Tying in the research, the way cargo ships are organized does have a reason. Heavy weights being placed near the sides and the bottom let the center of mass be positioned near the center line of the ship, where it is less prone to lean and bob in the waves. This information supports my hypothesis because the lower the center of mass is positioned in the ship, the more stable it is in the water. So the lessons learned here are that ship design can be based on many factors and have a wide variety of functions. Some ships have a broader, flatter bottom, while others have a sleeker, slender bottom. Most of these ships, regardless of the type of hull, have their center of masses very low in the ship to provide stability and balance in the water. These ships can also utilize ballast tanks to move their center of mass lower in the ship than would normally have. Other ships that do not utilize ballast tanks can use lead weights in their keel, a ridge that runs down the center of the ship from the front to the back, assuring stability.